I am a postdoctoral fellow at Lawrence Berkeley National Lab, and today I'm going to show a demonstration of using an R kernel with the Jupyter Notebook. And it's specifically applied to an analysis of water quality data pre and post fire after the 2017 wine country fires in Sonoma and Napa counties. And many of you probably remember these fires. They're one of the most devastating fires in the state of California, and they had quite significant impacts to urban and suburban, as well as forested and agricultural land within the area. So today I'm going to talk a little bit about an application of using US Geological Survey data to look at pre and post-fire water quality around the Russian River. And the Russian River watershed is the specific study site that I'm working at for my research. And the Russian River flows through many of the burn zones. So we think that we hypothesize that there will be major impacts to the water quality after these fires. So here's what you're looking at on the screen is my Jupyter Notebook, and I'm using an R kernel for this. And so I'm going to run through this analysis.
Before you run through it, I think you might just want to orient everybody towards the binder that you have on the website. The link is on the website.
Right. So I will point everyone to that binder link. I noticed when I tried accessing that binder link right now, it was a little slow. So it could be because there's a lot of users right at this time. So give it a little while, and probably in 20 or 30 minutes or so when users log off, there may be more time for you to check this out. So the binder link will allow you to run through this on your own. So as we run through this notebook, the thing that you can do with these notebooks is use libraries that are available to R, so you can install these libraries and use them within this notebook system. And so as I mentioned, today we're looking at the impact of these North Bay fires, and here are a few other links that can point you to GIS layers, drone imagery of the area, as well as a lot of interactive maps and photos to really see the impact that these fires had. And what we're trying to look at within this research is how these fires have impacted our water resources. So as I mentioned, our research at Lawrence Berkeley Lab, if you're interested to find out more of what we've been doing, here's a website to one of our press releases. And we have launched the pre and post-fire water quality sampling program with our collaborators in the Sonoma County Water Agency, as well as within the USGS in Boulder, Colorado. So the way that this is going to work is we're going to use some functions built by the USGS, and it uses their web services to automatically retrieve the data from their website. So the first thing are these functions, and that's kind of a nice way to retrieve data. You put some inputs into your function, you run the functions, and then you get outputs. So these are the functions, and I'm interactively running through this as we speak. So the first thing we decide is what stations we want to choose for the analysis. And I'm going to use the Guerneville station, which is along the Russian River, and it's called Guerneville site, this site right here, highlighted, and it's at the Hacienda Bridge. So we specify our input values, the station number or the site ID. We specify our start dates and end dates, as well as the parameter that we're interested in. And for this demo, we are going to look at pH, acidity levels in the river pre and post fire. So I run my input values, and then this is where we interactively fetch the data. So this line right here, get water quality data, that is calling the server and getting the data for the site and the start date and end date and parameter that I specified. So we fetch the data, and this is what the data looks like after retrieving it. You get your date, your pH values, and then some decimal year month sequences, as well as some statistics like the 7-day averages or the 30-day averages. And so here's a little bit more about what those components mean. I won't go into it now, but you can look at it on the binder link. So the really cool thing about using these notebooks is that you can then plot your data right after you've retrieved it. So here we're looking at a box plot of the pH data, and we can see generally by month, January is 1, February is 2, that pH varies naturally just within the year, with higher pH values, more basic values in the summertime, and more acidic values in the winter. And so we hypothesize, and we can begin to think about what's contributing to this in terms of rainfall, as well as the low flow season. Okay, so in this next section, I'm then classifying the data in a really simple pre-post fire based on the date. There are other ways to go about this, but for the purposes of this demo, it'll be a very simple date classification. And then based on that classification here, this is ggplot. ggplot is available in both Python and R. And so it's a nice package to look at data in this way, to simplify the groupings and the colors. So this is what we're looking at is pH, the same we were looking at before, except now it's classified. Post-fire is red, pre-fire is blue. So we can really see what those differences are. And one of the first things that we noticed is during the February timeframe that there was quite a large difference in the data. It shifted to more basic values. And so that's guiding us in our next steps and determining what else we need to measure and where we need to measure. And so we're going to be measuring additional, we're taking additional samples at various other locations across the watershed to really determine the source of this more basic water. And the next section, this is where we can start to look at the data in a spatial sense. So this function up here, this read water quality portal data, this is a function that was built to pull data not only from the USGS database, but from other databases like the STORIT database, the EPA database. And so you can see up in the left side where the little star is, it's running, and it takes a little bit of time because there's quite a bit of data. So I mentioned here in my comment that it could take a minute to fetch, and if you have an even larger data set, like if we ran this for a few years, that would be longer. So I think we've got a chat question. Let's see.
That was just.
Oh, it's just Matthias pointing out that the binder was down for a little while. That's why it's not working. So you can keep going, and I think people have an opportunity to go back and look at your code.
Okay, great. Yeah, I was wondering if everyone would be able to, if we were all logging on at the same time. Anyway, so here we can take a quick look at what this water quality portal data gives us. And you can see, what's really nice is you can interactively look at your data in this way, in this table format, and we can see that it's coming from NWIS as well as the STORIT and EPA databases. So the next thing that we're going to do is start to put together the data in a mapping context and look at, across California, what pH values have been generally in the past. And so that's what that first section was doing. It was taking the data and using some functions to look at the mean across the entire time series. And so here's, when we look at the mean, we can see that there's the STORIT database that it's coming from. And then finally, into this last section where I classify my colors, and then I'm running an interactive leaflet map. And the leaflet package allows you to create these HTML files and then run them within the Python notebook. So we'll let that run, and then Okay, there we go. So here's our interactive map, and this is showing pH values across the state of California. And I'll just zoom in a little bit here to the San Francisco area, and we can see you can click on the little buttons. Can I click on it? Yeah, you can click on the dots and see exactly what that pH value was and the site that it was measured at, as well as the type of site that it was measuring. So here it was a little lake, and here it was classified as a river or stream. And then finally, we go back to thinking about what's controlling our pH. And so the nice thing about these notebooks is we can interactively collaborate and work with other people and start to pull in other data sets to really understand what is impacting the pH in our river system, and how is the fires contributing to this. So if we think about a drainage basin and the concept of water flowing across a landscape, when water falls, it's going to drain into the soil as groundwater recharge, but it's also going to run off into the river. So when we measure water at any single point in time in the river system, it's a combination of multiple sources of water and multiple reactions that have taken place during the time that it has flowed within the landscape. So in the next steps that we're taking from this analysis is to answer research questions about what are the different contributions of surface water and groundwater to these systems, and we're using a numerical modeling approach. And one of the things that we envision in the future is to be able to use our models, these numerical codes, interactively within the Jupyter notebook, so we can have this all reproducible as well as interactive with various people. And finally, that's the end of my demo. So if you have any questions, feel free to contact me. My contact information is at the bottom, as well as my Lawrence Berkeley Lab website. So thank you.
Great, thanks very much, Michelle. We still have time for a couple questions for Michelle, if anybody wants to do that. And Michelle, if you can stop sharing your screen, we'll switch over to Valerie here. Thanks.
Okay, great, thank you.
I'm a complete noob to this. Hi there, Michelle. How do you find out about all these different packages that you use? So you talked about the mapping package and various other packages. Is that something you just go online and search for, or that's how noob I am?
Yeah, you're exactly right. It is the work that I do, I typically have a problem, and then I go online and on Google and I see if anybody else has tried to tackle this type of problem, and that's when I usually come across these packages. And the great thing about these packages is people put together them and they specifically solve whatever problem it is that you want. So with the mapping, the leaflet map, I found after testing many different packages that the leaflet was super easy to use with this USGS API data. So it was a very natural integration of that data with this mapping software. So it is a trial and error with Google.
Huh. So it almost makes me think it would be maybe useful to have a shared document where we capture this kind of research that we've done at the lab, because you put a lot of effort into figuring out the one that worked for you. And I would go and do the same, but you know, it'd be better to start with your experience. Maybe there's some way.
Yeah, on the Jupyter website, actually, they have lots and lots of examples, and some of them are earth sciences, but there are many other domains, and there's like tons of examples of packages you can use there. Yeah. So that's a really great resource for people who want to find out more.
Thanks, Michelle.
Yeah, thank you, everyone.
And just to add, a lot of the forums that Matthias and Carol also mentioned are really great. I've also found on social media, there's a lot of very quick replies, besides Slack, if you're not on Slack, as options. And we're hoping for the California Water Data Challenge that users focus specifically on looking at water and the challenge questions would discuss this and share lessons learned on the workspace and Slack channel as well. Thanks, Michelle.
Michelle, there was one more question for you, and that's the last one we'll take before we switch. So.
Okay, so the question is, when you work with different sources and try to consolidate in the one, do you read all the metadata upfront or use R to figure out the common data and have it do the work? So generally when I work with these different data sources, I do, just for my own understanding, I do try to consolidate them together. So I see what are the differences between my data and the USGS data or the EPA data, and it helps me better gauge some of the uncertainty in my own data. So that's one question if I'm interpreting that right. And then as far as using R, yeah, I pretty much use R to do all of the work in finding data. I rely on these packages that other people have built, and it makes my life a lot easier rather than having to reproduce the wheel and come up with or create my own code to do this type of interactive data fetching. Okay, so it looks like there's also one more question. So there's a question about the conclusion from this. So I will say that this is very much a work in process. So you're seeing science before any results are really clear and concise. You're seeing the newest results that are coming out of this analysis. So we haven't published this yet. So our interpretation is going to change once we start to really run the models. But at least in terms of pH, we are trying to figure out, using numerical models, why the water became so basic during that February timeframe. And the reason we're concerned is because it can have impacts on their drinking water system, as well as it's for fish. It can impact their spawning. So we're still continuing with the analysis to understand that.
Great, thanks, Michelle. And that's really why this is such a great tool, because you really can do exploratory analysis and actually just share even early results with collaborators or like with the public, like we're doing here. So this is why we scientists really love something like this. So next we have Valerie, who's going to be talking about the state water board's data sets. And that's on, so you can go ahead.
Hi, I hope everyone can hear me okay. Like I said, I'll introduce myself. I am Valerie Petela. I'm a DOE Mickey Leland Energy Fellow at Lawrence Berkeley National Lab this summer, and I will be completing my master's degree in geology from CSU Sacramento in the spring. So today I'll be showing you a Jupyter Lab display of a Jupyter notebook used to assess impacts to groundwater quality from produced water disposal ponds in Kern County, California. This research stems from some discovery made by Lawrence Berkeley National Lab about a lack of data and research regarding these produced ponds. So what is a produced pond? A produced water disposal pond is created after oil and gas production. For every barrel of oil produced, there are generally approximately 17 barrels of water produced with it. Some of this water is disposed into these produced ponds, which are unlined and specifically designed for evaporation and percolation into the groundwater. The produced water has a high TDS concentration, or high total dissolved solids. Now this is bad because these TDS can lead to health risks, which is why EPA has created a secondary drinking water standard for TDS at 500 milligrams per liter, and any groundwater under 10,000 milligrams per liter is protected as a possible source of drinking water in the future. The produced water from these oil and gas wells typically ranges between 10,000 and 30,000 milligrams per liter, but can be lower or higher depending on a variety of factors. So for your reference, I've included a map of California with Kern County shaded in red. Kern County falls within the San Joaquin Basin, which is where 80% of oil production occurs in the state. So to view this, I just had to import some basic libraries. This is an Python kernel that you're seeing in this Jupyter notebook. I won't be running through all of these because some of them do take a while to load, but if there's not already, there should be a link to the GitHub repository with a binder access through that point. So you can follow along or do it later on your own. But the whole point of this data challenge is to use public data. So that's what I have done for my research. I accessed the Central Valley Regional Water Quality Control Board produced pond list for 2018. Michelle used APIs and direct fetch from her data sources, but for all of mine, I directly downloaded them manually and read them in through Python script. The produced ponds were located through the Central Valley Regional Water Quality Control Board, and then the TDS measurements were located through two different state water resources. The first link I used is provided by the State Water Resources Control Board. This is all of the data that's in the Gamma database. I downloaded the Kern County all data sets. You can see there are different sampling agencies that contribute to this. And then that includes 245 chemicals, over 100 years of sampling, and thousands of wells. The second link that you see there is for this GeoTracker Gamma interactive map, where you're able to filter your data. So I chose Kern County because that's what I'm looking at, but there are different filters that you can use to access different data. You can draw shapes if you know a specific area that you want to get constituents for. I chose all data sets to get the most bang for my buck, and I'm specifically looking at total dissolved solids, but there are, like I said, over 200 chemicals that you could choose from to download. So once we have all of our data, we're able to sort of sort through it and start looking at it. The Gamma all data file was too big to load in any text editor or Excel, so that's what Python's here for. It's much more powerful. So we were able to read it in and make some changes so that we could write easier script later on, like adding columns, renaming them so they're a little bit cleaner. And then using that, I was able to plot a map. Now this pulls directly from an ArcGIS server to get a nice, pretty street map. There are many different maps, as you saw through Michelle's. There's a couple different things that you can do to get this, but you just plot it and you can follow along through the binder. However, this map shows the TDS concentration, TDS measurements by year. The lighter colors are older samples. The deeper red is more recent samples. And these all fall within Kern County, which is this purple county line that you see along the outside. The green dots are the produced pond locations taken from the Central Valley webpage. And these black polygons that you see within are oil field boundaries that are uploaded from a shapefile retrieved from the Department of Conservation, Division of Oil, Gas, and Geothermal Resources website. So now that we know when our data was taken, we can begin to look at what the sample results were. So just to see what kind of data we're looking at, you see that we have a range from 0 to 231,000 milligrams per liter in those sample results. We have a median of 345 milligrams per liter. So while most of our points fall within an acceptable range, there are some of those that far exceed what is acceptable by the EPA. Now that because we have such a big range, we weren't able to do a simple gradient like we did for the first map, so I had to create these bins that divide up the concentration into reasonable quantities so that we're able to manually set the colors, which here I use the color codes. And so that is used to create this map, which I'm not sure you'll be able to see all of it with this view. Let's try to zoom out a little. Let's make it worse. Well, what you can see, or you can follow along in the binder. So the cooler colors are lower concentration TDS, and the warmer red colors are higher concentration TDS. You may notice that the higher concentration TDS fall along the west side of the valley, which is where there are more produced ponds, but those are not necessarily related. The higher TDS along the western side of the valley is most likely due to the geology of the area. The western side of the valley is composed of marine sediments, which undergo geochemical reactions and mobilize the salts and create higher salinity water naturally. So now that we know when and what the results are, we can begin some actual analysis. Here I've chosen to use the main candle statistical test, which is a non-parametric test good for time series data. I've included a link for where I've found this function, and I've included it here for you guys to view and reproduce for yourselves. Tested it, made sure it worked. You see what kind of output it gives us, and now we're able to use it on the real data. Kind of skip through some of these basic filtering principles, but we filtered out our data to where there was only groups that included 3 or more data measurements per well ID. This is so that we have enough data points to get a trend to see if there is increasing or decreasing, and then we're able to run the statistical test. Now this is a loop that it creates a CSV file, and then it pulls out the data, runs the MK test on every individual group that has 3 or more sample points, and writes the results to that CSV file. If you are running this on your own, it takes about 10 minutes on my computer. It may take longer or not run on yours. So I have included the results file in the repository as well, so you can skip that step and move along. But you can see here that the results file produces some extra characters and some white spaces that make your data hard to read later on. So I used OpenRefine, which is a text editor. I found it really great for finding typos in data, especially if you're social sciences. If you spell a name or a location wrong, it's good for getting those typos out, or extra commas. And I've included the link here so that you're able to download it and check it out for yourself. So we clean it up using OpenRefine. It's much easier to deal with now. And then we only want to look at places where there are trends. So we filter it out, and we only now have our increasing or decreasing trends. You'll notice that the results file doesn't have any of the coordinates, so we need to add those back in to get the locations where those trends exist, which you can now see here. And then we can map them to see where our trends are. I should note that there was about 1,500 possible trends, so 1,500 places where there were 3 or more TDS measurements. However, only 140 had increasing or decreasing trends. So we plot those here, and you'll notice that there are not 140 red dots indicating a trend. So I was very confused by that as well. But you will see that there are these 14 locations intermingled with these oil field boundaries and produced ponds that show a trend. So upon further investigation, I looked into my data sheet. You see there's a column for well name, well ID, and then the coordinates. I did a test to see how many of those were unique. Since well ID had the least amount of unique values, I assumed that that would be a unique identifier, because different sampling agencies could have different names for the same well ID, but they would be at the same location. So I assumed that well ID was correct. However, I received personal communication yesterday from the State Water Board that if you are looking at this data, it's important to note that the well ID and well name need to be combined to have a unique identifier. And the locations may still come up the same because there could be nested wells, or different agencies could still be using different names. So this research will need to implement that change. I just didn't have time before today. So now that we know where our trends exist, beyond knowing which wells are unique, I thought it would be good to visualize what some of those data points look like. So this is all of our data from that gamma data set that includes all the chemicals and all the dates. This is just the TDS concentration over time. You have TDS concentration in milligrams per liter on the Y. You see this high point of our 231,000. And our date is on the X. So you can see that there are an increasing number of TDS measurements as time goes on, which is great that our water quality is being measured and managed more. And it's great for this data challenge as well. And here I've included some plots of some individual well IDs. Now we know that this needs to be combined with a well name to make it unique. However, I just pulled a couple out so you can see what kind of data we are looking at. So this, through the MK test, is an increasing trend, but you can see that we have systematic sampling that's pretty regular, and there's quite a few data points for these 30 years. This is another increasing trend that has just a few data points for those 20 years. And this is a place where there is a decreasing trend that also just has a few data points for a few years. So you can see there's a wide range of what's available out there and a little bit of how to use it. This is what I've gotten for you today. This is a preliminary analysis. It is in no means finished, and all of this is subject to change, especially after communicating with the State Water Board. But I'd like to thank you guys for listening and thank this Water Quality Data Challenge for making data more public and transparent for the rest of us. I'm open to take any questions.
Great, thanks, Valerie. Anybody who has questions, please pop it in the chat window. I also do want to point out while you're doing that, for the TDS data, the data.ca.gov has an API for some of the constituents, not for all of them. They actually, made that available when we requested it. There was an API functionality that they made sure it was enabled for this challenge. So I encourage you all to go to data.ca.gov and look at the water quality data out there, and try to retrieve it programmatically so we don't have to, download this huge file and then sort through the constituents for, if you're looking for, something in particular that you're one or two constituents you're interested in. All right.
Thank you for sharing that. I will keep that up for those of you that can't see the chat window. Meredith said, a note for all teams working on data visualization and analysis, red-green color blindness is the most common. So there's a link to navigate this to avoid that issue. Thank you, Meredith.
And someone asked for the data.ca.gov link. That I just posted that in the chat window.
On that, you mentioned that there's a well ID and a well name. They said you have to combine the two to get a unique
identifier.
That would make even, it seems like that would make the problem even greater of having 14 locations, but 145 trends at those locations. In the sense that, you're basically doing kind of this many-to-many join. I don't know. It seems like that wouldn't solve the problem. Did you have any insight specifically as to why there's like 10 temporal series per location?
Right. So I haven't had a chance to look at it since they said that to me. They suggested that it might be from different agencies having different names, so even combining the well ID and the well name would not make it unique. Oh. And also the possibility of nested wells. So there would be, but the well ID and well name would be unique for the different nested wells, but they might still all exist in the same location.
Okay.
Great, thanks. We will move on to the next presentation now. So what we next have is Kitware. We have John Turnelet and Ashish Chowdhury from Kitware. They are going to be presenting how to use this example that Valerie just presented on the oil and gas produced water disposal, but they just took our base map and made it more interactive. So they have a really neat demonstration here for you with their tool called GeoNotebooks that can then be used to do some more of this interactive analysis. It's a different way of doing it from what Michelle showed earlier.
I will actually go ahead and answer that last question that somebody else just posted. They said, any specific reason for choosing Kern County, or was it just a choice to deep dive the analysis on a point and then extrapolate the same idea to the next level? Kern County is the biggest producing county it's where 80% of oil production occurs, and that's where a large portion of produced water disposal ponds are. So just having the availability of these places and the likelihood that they might interact and contaminate groundwater just made the most sense.
Yeah, and I can chime in. This is Preston Jordan. Kern County has more oil and gas wells than any other county in the United States. So it's a great place to do this work.
take a couple minutes break while we're transitioning over to Kitware. Thanks, everybody. And you can feel free to keep posting your things in chat, and we'll message you back even if the other presentation is going on, if you have questions. John, if you can share your screen, that would be great.
I think I've got it, Charu, just showing the your outline there, your agenda.
Okay, great. So we'll reconvene at 11:20, I guess, according to my agenda. So
Still on time.
great. Thanks, everybody, for staying on time. And Meredith just pointed out on the Slack channel that if there are people who are using the state's water data data sets, please ping them on the Slack channel if you have any issues, because the state is looking for feedback about the usability of their data sets. And so they actually, I can tell you from my personal experience, they've been really responsive about getting back to us about questions and about any issues that we found. So this is really a great opportunity for you to provide feedback directly to the state.